for coming. Gideon De Beer is a final year MSc student at the SAO at UCT, and his MSc research involves multi-wavelength data from near-cut and optical surveys, and he is investigating the population of extended radio sources in and behind the small Magellanic Cloud. In addition, he has created his own citizen science project, and that is what we will talk about tonight. Thank you very much for coming.
Thank you very much, Christian. Hello, everyone. Thank you for joining in person and online. Right, so as Christian said, tonight I will be talking about radio astronomy and about citizen science and how pretty much anyone can contribute to astronomy by becoming a citizen scientist. So for tonight, summary for tonight, I'll be talking about observational astronomy in general, then about radio astronomy a bit more specific, and then citizen science and the Zooniverse platform, how you can become a citizen scientist, and I will present two projects, the Galaxy Zoo project and the Radio Whispers project, which is my very own MSc data on a Zooniverse project. So observational astronomy, it's all about the gathering and studying of cosmic light. So you gather light through a telescope or through an instrument that can see in certain wavelengths, and then you kind of count photons. That's the basics of it. On the screen here, you can see the entire frequency range of light that we can analyze. And that little speck in the middle with the color and the rainbow, that's the visible spectrum. And that is what all optical telescopes use and what optical astronomers study. And it's just that little gap in there. So the rest of the whole spectrum, it can't really be gathered with conventional telescopes. You need to use specialized equipment and very weird kind of equipment that doesn't look very nice always. Sometimes you can't even look at this kind of light from the Earth because the atmosphere just blocks it out completely. So you have to use space telescopes instead of terrestrial telescopes. So in observational astronomy, it's also the figuring out of how things out there, how do they work? How did they come to be? What will they be in the near future, in the far future? It's about what influence they can have on us. And when I say us, I mean the past, present, and future us. When I talk about the past us, I'm talking about things like the 1859 Carrington event. For those of you who don't know, the Carrington event is the most famous solar flare event that's been recorded in recent history, and it's the event where all of the, I wouldn't say all the electronics, but definitely all the electronic modes of communication of the 1800s was completely fried by the charged particles that came from a solar flare that we didn't see coming and we couldn't predict, and everyone was busy on their telegraph machines, and then everything just caught fire. What also happened is they saw the northern lights and the southern lights, the auroras, very close to the equator, and that also just doesn't happen. And we've through studying these kinds of events, we've developed early warning systems for solar flares for asteroids that are near Earth and might be dangerous. Some asteroids are far away, but they're still on either a collision course with our planet, or they will pass close enough that they are deemed dangerous. It's also about what influences we may have on these things out there. So things like finding life elsewhere and how we can kind of verify that we've actually found life. So in missions where they bring back samples from a different planet or somewhere outside of our atmosphere. They have very, very strict rules about sanitation, and everything needs to be sterile on the whole journey until someone actually opens that container that has the sample. And that's also done in a completely sterile room, sterile environment, to ensure that we don't actually introduce anything from our side to that sample. It's also about finding life elsewhere, maybe finding us, you know, the whole SETI program, searching for extraterrestrial signals in the cosmos, signals that look like communication signals, specifically modulated signals that would indicate not a thing, but communication. And it's on all these scales, you know, it's planets and stars, which make solar systems, and then collection of solar systems and dust that make galaxies, and collections of galaxies and all of their influences that create the cosmic web on the bottom left over there of the observable universes. And these are orders of magnitude larger or smaller than the previous or the next. With radio astronomy, going into specifics, it's looking at light with very long wavelengths and low frequencies. So these, this light is on the lower energy side of light, but that doesn't really mean that the events that spawn them are low energy at all. Because some of the most brutal and beautiful events that we have witnessed are very, very bright in radio. But that's not because they are thermally very active, it's because the radiation that they give off is called synchrotron radiation, and it's actually produced by electrons that are accelerated in very strong and twisted magnetic fields. So things like supernovae, the jets from the centers of active galaxies, and spinning neutron stars that produce these kinds of synchrotron radiation that are very, very bright in radio. So we have in South Africa the largest radio telescope, you could say. But it's not really a telescope, it's a collection of 64 dishes that's called the Meerkat telescope in the Karoo. It's close to Carnarvon. And the very nice thing about this telescope is it's an internationally acclaimed and sponsored, and everyone's working or trying to get time to work on this telescope. And since it's been built in South Africa, we get a very large portion of the time that is allocated as science time to be spent on South African projects. It's also very nice because it's an interferometer, and so you know it's an interferometer. Okay, what does that mean, right? But this is where you do the analogy. Thanks for reminding me. So with interferometers, you can think of it as this radio tower icon here at the top being your source, and it's, say, a radio station that's playing a certain song. And these three radio receivers here are your dishes. So each of them are listening to the source, and each of them at some point in time get the same signal or the same song, as it were. And then they communicate with each other to say, okay, listen, I found this song, or it sounds kind of like this. Did you also hear or see something like this? And then all of the other telescopes will say, yeah, I think I heard something that sounded like this. Then they all kind of combine what they hear to make this interference pattern. That's where the interferometry comes from. And the more signals you have to interfere with each other, the clearer your signal becomes. And the longer you listen to it, the more you can see or hear, as it were. Nice thing about interferometers as well is the further the distance is between two dishes, the more detail you can see. And the closer they are to each other, the more sensitive to very non-luminous kind of characteristics you'll be able to see. And what makes the meerkat so very, very strong is that it can do both of those things really, really well. Because you have this core in the middle of meerkat. It has a bunch of dishes, and they are used for the short baseline sensitivities. But then you also have these dishes that are really, really far from one another that can really make out those finer details and pinpoint the location of certain sources. So once you start observing with an interferometer, it creates what they call sensitivities on a VU axis, or the UV plane. It's not to be confused with ultraviolet light, it's just called the UV plane. And the longer you observe on one spot, the more coverage you get on this UV plane. And the more coverage you have, the more detail you can see, and the deeper you actually go into space. Right, so now citizen science, the Zooniverse platform.
Can I ask you?
Yes.
On the previous slide. These lines that form around the object, is it due to what?
No, this is not lines around the object. These are lines tracing the UV plane. So if you can think of this as being like a filter that you put over a picture, and these lines are the parts of the picture that you can see, then that would be what would be revealed. So it's like the longer you carve out those pieces of the picture, the more of the picture you can see. Yeah. All right. So citizen science and the Zooniverse project, it's on zooniverse.org. You can Google it, you can use this QR code, you can just go to the website, and it's free, and it's free to register, it's easy to register, and there are many, many, many projects to choose from. So the way it works is the scientists or astronomers, they gather data and they realize, oh, I've got way too much of this to actually look at. It'll take me more than a few lifetimes to actually get through all of this data. They then say, okay, let's create a Zooniverse project or a citizen science project and ask volunteers to look at the data alongside these scientists also looking at the data. These projects then have very clear instructions, they have interactive features, volunteers can talk to collaborators on the data, and through these collaborations, the project is improved on the go. Volunteers can then become citizen scientists who provide classified data from the raw data given, and this is usually in the form of labeling data and telling the scientists just like, what do you see in an image or a signal or a graph or anything like that. Then scientists can draw statistically sound conclusions from these output data, and sometimes they can notice, oh, okay, but now I have all of this data. I still have this Zooniverse project, so maybe I can just put it back on there and say, okay, but what do you think about these results? Does it look like this, or does it look like that? Things can go in a loop. And that usually leads to publications, and through publications, the citizen scientists can then get kind of bragging rights when these things come into the public spheres and say, I helped with that project. So when becoming a citizen scientist, anyone can sign up to Zooniverse. Everything is free, everything is open source. Some projects have been made available on their mobile app. So you can even do it on the go during your lunch break. Have a go at classifying data to your favorite project. You can just head over to the website, get an account, and start being a citizen scientist. So the Galaxy Zoo project, it started in 2007 before Zooniverse was even a thing. It led to the classification of over 1 million galaxies very early on, and I think the official number now is around 1.4 million galaxies that have been labeled and classified. So these results have been very, very useful to the people who are working with AI and training AI to better their ability to be able to recognize patterns and identify things in images. And it's actually the project that led to the creation of Zooniverse. And down here, I've put some of the categories of projects that are available on Zooniverse. So you can take your pick. It's a whole world of projects out there that need classification, and yeah. Now we're coming to my Zooniverse project. It's called Radio Whispers from Our Neighboring Galaxy. It's a new project that uses Meerkat and Supercosmos all-sky survey data. It's looking specifically for SMC, small Magellanic Cloud, extended radio sources using these deep Meerkat radio images that I'm using for my MSc research. So again, you can scan this QR code, or you can Google Zooniverse Radio Whispers, and my project should be the first one that pops up. Or you can follow this link and type it in. Whatever works fastest for you. So I've been having this presentation with this background, but I haven't told you that this background is an actual image from Meerkat of the SMC. I just wish I did not make it so dim. It's actually quite magnificent. The small Magellanic Cloud is an irregular dwarf galaxy. That's not our closest neighboring dwarf galaxy, but it's one of the top 5 closest at 60 kiloparsecs away. And if you zoom into that little part there, this image on the left-hand side here is what you will see. And I have taken this image and I've overplotted these contour lines in green that indicate levels of radio flux density. So these contours are kind of like what you would find on normal road maps that indicate elevation above sea level, only they are indicating where the actual bright radio emissions are originating from. These images were also sent through a software called Gideon, which is very good at creating catalogues of point sources from any kind of FITS file from any astronomer. And while it's very good at locating point sources, I'm not specifically interested in point sources. I'm interested in extended sources. But what it did is it kind of clumped up all of these point sources in locations where you have extended sources. And I had a lot of these. So that's why I made a Zooniverse project to get some help with classification on this data. So this is one of the sources that I'm looking at. On the left-hand side, you'll see the radio image with the radio flux density contours. And on the right-hand side is the optical image from the supercosmos or fluxway, with the radio contours overplotted on the same location as the radio source. So what I did here is you can see these two nice blue radio point sources that were identified, but they're actually part of a larger system of one radio source. And this is the kind of thing that I need help with identifying. This is another one that's quite interesting. It looks like a point source in radio, but once you take a look at what the optical field looks like, there's actually two sources inside. And there's two things that could happen here. It could be either one of those two sources, or it could be neither, and it's a background source that's not visible in the actual optical field.
And those sources, are they like stars or?
Most of them are stars here. So this is one that looks like a point source in radio, but once you look at it in the optical field, it clearly shows that it's probably a distant galaxy, and it's edge on. So it's probably not an active galaxy because the radio does not show any kind of jet morphology or stuff like that, but the radio core of the galaxy is still visible. This is a view in my actual project of what these sources look like. This is an example of something you would choose to be an extended radio source. That's the very first question that you will be asked, to say if looking at the radio contours, does it look like this little gray beam size on the bottom right of the actual image? And if it does, it's very likely a radio point source. If it doesn't look like that and it kind of extends beyond the blue ellipses, it would be marked as showing extended morphology. Well, in that case, you will then be asked to say, okay, but is this source that shows extended morphology, is it part of some collection of sources that have been identified by AGN? If it is, you'll say yes, and you will click on all of the sources or the ellipses from AGN that you think are associated to that source. In the next part, you will be asked to say, okay, but looking at the background optical image, does there seem to be an optical source inside the central blue ellipse that seems to be related to the radio source? If there is, they will be given options as to what it looks like, and there's no correct answer to that one. I'll come to that a bit later. But if there's not, you just say no, and you continue to your next source. In this case, it's a radio source that shows extended morphology, but it does have a central source in optical that seems to be associated to the radio source. And the options here will be, does it look like a point source or a star-like source? Does it have a bright core surrounded by a kind of a gassy region? Is it kind of just a gassy region? Or are there multiple sources inside that could be associated to that radio source? And there's also one for an oddly shaped or not sure, in case you find something that it doesn't really match with the other four choices. This is an example of a radio source that you would classify as looking like a point source, since it looks like this gray beam in the bottom right hand corner. And it has no clear optical counterpart. And then this one also looks like a radio point source, but the actual optical source looks like either a gassy region or multiple sources inside probably, or it can also be one with a bright core surrounded by a gassy region. Either would be be fine. In conclusion, anyone can contribute to science and astronomy. Citizen science is a fun and interactive way to actually do so, while also learning about new things in any of the categories of citizen science projects that you choose. The advancements in astronomy have led to the need for processing big data, and the words big data are in quotes because big doesn't really own up to the scale of data that has been needing to be processed. Then AI and machine learning algorithms also need more research and development. That's also where citizen science and labeling data comes in very handy, because these machine learning algorithms actually need things that are correctly labeled to be able to train on them to say, okay, this is what you're looking for, and this is called that. So that when they are showed something that they haven't seen before, they'll be able to identify what that most likely is based on what they've seen. So yes, please share the QR code and the link to anyone that might be interested. That's all, folks. Thank you.
Thank you so much, Gideon.
That's okay.
Laura's open for questions.
Can you go back a few more slides?
Yeah, sure.
Let's go to the citizen science. Just stop over there, sorry. No, the next one, I think it is. Yeah, something like that. It says if you get that blue region, that blue region is now, it's a source that has got multiple probably sources.
No, okay, so
Why is it made blue?
yeah, okay, so the blue solid regions are those identified by a gene that have high signal to noise in radio. So that just kind of means it's much brighter than what's surrounding it. So that is very likely a detection instead of just being noise. Where the dotted green regions are sources identified by a gene, but the signal to noise is not high enough to be certain that this is a detection.
Okay, yeah. And the next one? So I'm trying to learn this one now. So there you say in the blue region with the top red arrow, there is a source on the left hand side.
Yeah, there's a source on the left.
That's not the source.
Yes, it's on the left hand side, but it needs to kind of be centralized.
Oh yes,
to be associated to that source. If it's close to the center and you think it might be associated, you can still say yes. I think this source is associated to this thing, and that would be completely fine.
Got it. Thank you.
No worries. Any more questions? Anyone online?
I have one. I always like to ask a question to people portraying universe projects. I mean, obviously, you must be confident in the volunteers doing the right thing. So, do different volunteers classify the same sources?
Different volunteers classify the same sources, yes. So in the case of my project is I show the same source to 10 different volunteers. So that I can get that statistically sound. Okay, so if everyone agrees 90% that this is an extended source, then I'm pretty sure that, okay, this is an extended source. If it's 50-50, I kind of need to go look at it myself and cast that kind of source aside a bit so that I can actually ensure that this is what it's being portrayed to be. So yeah, every source is being shown to 10 unique volunteers. And then when 10 people have classified that one source, it gets retired. Then no one looks at it again.
Okay. Can you go back to your QR code?
Mine?
QR code slide.
QR code, yeah.
The photo of the
No worries.
How many people signed up for your project?
At the moment, I've got, I think, 14 people. And I need a lot more. Yeah.
But does it grow? Is there
It's growing steadily, slowly but surely.
And how much data do you have to?
So I've got 14,000 odd classifications that I need, and I'm sitting on 2,600 odd classifications at the moment. So it's almost at 20% done.
What is your outcome of this, if I'm asked?
So the outcome of this will go to my research for my master's project, where I am busy building a catalogue of extended radio sources in the Small Magellanic Cloud. So that will be kind of a list of where they are and possibly what they are and what they look like.
But you can't say what they are.
Not yet, no. I mean, if it's obviously a galaxy, then I'll say, okay, this is a radio galaxy. But if it's something obscure, then I'll just say, okay, there's something here. It's got extended morphology. I don't know what it is yet. Further research needs to be done to identify it. Yeah.
You look at these small and large metallic clouds quite a lot from our observatory, but with the telescope, of course. But okay, we can't see that obviously. Our other radio telescope. But yeah, okay. So I've heard, maybe you know, that there's something behind small metallic clouds.
No, there's loads. Yeah.
I mean, they said it's not a galaxy that behind.
There's loads of galaxies behind Small Magellanic Cloud. Yeah.
But they don't interfere with the metallic cloud.
No.
That we can see.
No.
It's too far back.
It's way too far back. Yeah. Now that's one of the main goals of my research, is not just looking at the stuff inside the Magellanic Cloud, but the stuff way behind it. Yeah.
What is the exact difference between artificial intelligence and machine learning?
So artificial intelligence is the term that I feel like it describes more the thing than how it's trained. So it's if you have an artificial intelligence, it's something that can either think for itself in a certain way. When you give it something, it knows what to do with it, without you interfering and telling it what to do. And machine learning is what AIs have to go through. It's the process they have to go through to actually gain artificial intelligence.
Okay, so by machine learning it becomes artificial intelligence.
Yes. Thank you.
Are there any other questions?
I see there's one thing on the chat.
How can we get hold of you if we want more information?
I will link my email. I should probably do that in the slides, right? Yeah. I can send my email to Christian, and then he can spread it around. Yeah.
Thank you.
Nice. Thank you.
I've been, or I am, or was a scientist. I did a lot of galaxies and moon craters many years ago. It was quite an interesting exercise.
Now we try to make the citizen science projects actually not just about classifying; it's about learning and seeing interesting things. Yeah.
So it will be interesting to get your conclusion at the end. What happened with your project?
Yeah, I'll have to come again then. Yeah. When it's done.
And show your project in detail.
Yeah, definitely.
I heard a program on the BBC World Service last night about quantum computing. They reckon they might be available in about 10 years commercially at this time. Would they help your system in any way?
Oh, loads, yeah. Yeah, quantum computing would actually work really, really well with AI, because it would speed up the learning process by orders of magnitude. So you could, if we probably already have, but if we could code an AI that uses quantum computing, it would just learn like that. And if you ask it a question, it'll be instant, like, yes, I know what this is, or this is the answer.
They didn't make it exactly clear, but how would you program a quantum computer?
Okay, that I do not know. That I have no idea. I just know they're really, really fast.